increase the size. Okay. So you have already seen how you can design finite state machines. So now the next aspect is how we can minimize those machines. Now before we go into that, let us just consider a few other aspects. What is that? Okay. So you have already, one second. There are certain things that I have to do, otherwise it doesn't work. Let's say. Yeah, so let me pose a simple question to you. You have already, I think you have already studied the course on automata theory. So there you have studied finite automata, right? You have studied finite automata. And over here, what you are studying are finite state transducers. Are you okay with that, first of all? Do you appreciate that what you have studied here so far are really finite state transducers, and what you have studied so far are finite automata? I mean, not so far means in your other course on what is that course?
Flat.
Sorry? Flat, yeah. Flat. In flat, you have studied finite automata. So, are they computationally the same, or are they different? Can someone try to answer? Are finite automata computationally equivalent to finite state transducers, or are they different? Can you just try to, can you think and tell me? Someone? Yeah? Yeah, come on, just try. I mean, there is nothing wrong in trying. Why don't you just try? Just try to answer. Right or wrong, that's not so important. Just try to answer. Someone? Ritoman, you are, I think, would you like to try? Are these two computationally the same, or are they different? Yeah? Who will try to answer? Just try to answer.
I think same.
Okay, so if they're same, so in that case, a finite.
There should be a conversion.
Okay, so a finite automaton is defined by what? You don't have any output alphabet in a finite automaton, do you? In a finite state transducer, you saw that you have an output alphabet, right?
But sir, like in a Moore machine, is on, like the states have the state name and the output.
Yeah,
So
but you
that can
still
be
have,
combined to think as a state.
no, no, you still have an output alphabet. You still have an output alphabet. Moore machine or Mealy machine, you still have an output alphabet. So, whereas a finite automaton, the definition at least doesn't have any output alphabet. So what do you do about the output alphabet? So if you can just try to draw a diagram. So I mean, if you just draw a diagram, let us just see. I mean, your finite automated looks something like this. You have an initial state, and then you have, transitions on uh, X, some transition on Y. Yeah, there is a lot of noise. So, yeah, and then you might have some looping and all that. So is it, and you have a final state. So this is what a finite automaton looks like. All right, and what does the FSM look like? You still have an initial state, but your transitions are a little different, right? So you have X, A, and you have Y, B, maybe something like Z, C, something like that. So this is your finite state transducer. So are you okay with this? I mean, I've just drawn some representative diagrams. So are you okay with this? This is what a
Yes.
finite, yeah. So so now what you can see is that, this, or maybe I can just use a different pen. So these can be your, you can consider these to be your, symbols. So you can actually absorb your this input output combinations into your, you know gamma dash. So you can construct it. So now you don't have you don't have any problem with the output alphabet anymore. You are able to absorb, the input output symbol pairs into a new input alphabet. Initial, you still have, this initial states, so that's not a problem. But you might have noticed that in a finite state transducer, you do not have any final, you don't have a final state, do you? Do you have a final state in your finite state transducer? You may not have, right?
No, not really.
Yeah, but you can designate. So actually, how do you designate? So that designation, so usually that input, the output, the output that you have, that usually indicates. So, for example, some of these outputs might, indicate some intermediate output, and some of these outputs might indicate an acceptance. You can say that means you have got the right kind of input. So that way you can, so where you have the right kind of output, you could, or maybe I could just, so you could, designate some of those states as final states. That means some of these states could designate, could indicate that you have received the right kind of input. So what you can see is that, you can make some small transformations on a finite state transducer so that it actually, looks like a finite automaton. So those are computationally equivalent. You might have to do some state splitting and all that. All right. So I hope this is clear to you. So finite state transducers and finite automata are computationally equivalent. Alright. So now let us go over to another question. So these are finite automata, right? So finite automata means fixed, finite automata, or if I just write finite automata. Finite automata means a fixed number of states. Okay, so you have a fixed number of states. Let us call that T. So some, because it is finite. Your set of states is finite. So you have a certain number of states P. All right. Now let me ask you one question. You have designed a serial ladder. Haven't you designed a serial ladder? Yes? You have already done that assignment in the lab, in fact. You have designed a serial ladder, right? So, my question is, so this serial ladder can add two numbers of any length, right? So serial ladder can add two numbers of any number of bits, or of any length, let us say, any length. Is that okay? Are you okay with this claim? Yeah, please answer. Are you
Yes,
okay?
sir.
Yeah, you're okay with this. So all of you, you can. All right. Now the next question is, so this is the question that I am posing to you. What will be your answer to this? Yes? Again, just see, just tell me something. What will be your answer to this? Can you design a serial multiplier to multiply two numbers of any length? Yeah. What is your feeling, or what can you say about that? Someone can volunteer to answer. Who will answer? Can you reason about it? Yeah. Someone try to answer. Say something. And then I'll only have to call out someone. Shivam Singh, would you like to answer? Shivam? Yeah, Shivam, would you like to try? Shivam, are you there?
Um, Hello.
Yeah. Tell me. Would you like to?
Yes. Sir, I wanted to ask that if you are mentioning that of any lens, so we are
Yeah.
using this circuit for any lens.
Yeah. Just reduce your. Okay. I mean, your. Okay. You carry on. No problem. Yeah. Just carry on. Okay.
Yeah, I guess we can create a multiplier like if we know a particular length, like for a length 2, we can design a multiplier for that length 2.
No,
But if we know,
no, for any length. For example, a serial adder, you have already done the experiment in the lab.
yes, yes,
Using that serial adder, you can add two numbers of any length. All right. 10 digits, 15 digits, 50 digits, 100 digits, bits. You can actually add. My question is, can you design a multiplier which can, yeah.
but the thing is like if I remember correctly, like if we are adding a 10 digit and we are adding a 20-bit number. So, if I remember correctly, the circuits required to add them were different, right?
See, you have to see.
Logically, we can multiply, but
Wait, let me let me tell you something. See, when you say that you can do something, that is in a way relatively easy, because you can present a design and say that, okay, see, this is a design and this is this is doing it. Now, so of course, if you think you can design, you can definitely present a design that works. But if you think that it can't, if you think that it can't, the work cannot be done, you cannot give an example of some circuit which fails to do it and say that it can't be done, because there is always a possibility that you can design a better circuit which can, right? So that is not the way to answer, because I mean you should be aware of that at this stage. It is more difficult to answer, this negative claims. Positive claims are relatively easier to answer, because you present a solution and you say that, okay, this is a solution, it does it. So, so that is relatively easy. But suppose something cannot be done, so you cannot give an example of something that cannot do it and say that it cannot be done, because it is always possible that you might be able to find a solution that actually works. So you have to have different kind of arguments if you want to say that something cannot be done. Those are actually a little more. But what I'm saying is that you have already studied this. That's why I'm asking this question to you. You have already learned how to give these arguments. I mean, you have already. You should be in a position to answer this question. That's why I'm asking this question. So, would someone like to try again? So, I'm just. So, yeah. Would anyone like to try again? Yeah, I think you're a bit off the mark. Yeah. So, would someone like to try again? Yeah. Or should I call out someone's name? Okay, so I can see the picture of Satvik Bansal. So, Satvik, would you like to try?
Yes, sir. I was the one who tried earlier. Yeah, I just wanted to make one more point.
Yeah.
Like maybe what we can do is just create a shift and add multiplier. Like
First of all, tell me whether, yeah, Satyik, are you there? Yeah. So first of all,
Someone is removing us.
no, no,
Continuously,
don't
someone is removing us.
please don't remove.
Yes.
Yeah, yeah, don't remove. Okay,
Hey,
Satyik.
CRM, can you just do 1 minute? Your slide will be off for a little bit. I
No,
am making you
no,
the sole presenter.
no problem, no problem. I think they will be able to hear me, right? So.
They'll be able to hear you. Huh.
Yeah, yeah. So I hope Satyak is back. Anyway,
yes,
first of all, let me ask you: do you think it can be done, or it cannot be done? First, answer that question.
it can be done. It can be done.
It can be done. All right. Okay. So I think there you are wrong. It cannot be done. First of all, so it cannot be done. Uh, yeah, but now you try to answer. So because yeah, it cannot be done. Now you try to answer why it cannot be done. See, one very intuitive reason is that, see, when you add two numbers, what is the size of the result? The size of the result can increase by only a fixed number of bits. Basically, it can increase by 1 bit, isn't it? So, so, so if you think of dealing with a finite automaton, then it's relatively easy to handle that. But when you multiply two numbers, let us say two numbers of p bits, then what is the size of the result? The size of the result is almost double, right? It's almost 2p bits. So using a finite automaton, it is difficult to keep track of so many bits because you're not having to keep track of a fixed number of extra bits or anything. You are having to keep track of number of bits that is proportional to the input. So if your input is of n bits, if you are multiplying two numbers of n bits, then your output is almost 2n bits. So so now can you try to answer? So actually, I mean you studied this some time back. Do you still remember anything about the pumping lemma? Yeah.
Yes, yes.
Okay. So if you remember about the pumping lemma, you should actually be able to use the pumping lemma to prove that this cannot be done. So can you try to do it? I mean, you can do it, or anyone else can also do it. That is fine. So, so, so can you use the pumping lemma? So, so you can, take a very simple case of multiplying two numbers. You don't have to take a difficult case. You take a simple case of multiplying two numbers and apply the pumping lemma and show that it cannot be done. It's as simple as that. So can you try? Because this is very important. I mean, there are concepts which actually span across the subjects. So it is not that this pumping lemma is only applicable to flat. It is also applicable to your logic design. So yeah, so can you try? You or anyone else for that matter. Yeah. Can you try? Just try, and are you trying? So first of all, you tell me which two numbers would you like to take as an example? I think that is a good starting point. Which two numbers will you try to take as an example? assuming that, let us say that your machine, your pumping length is say P. I mean, that kind of boils down to saying that your machine has P distinct states. Okay. So which two numbers do you think you should multiply? It should take, consider for multiplication. Yeah? Can anyone suggest? Shayantan, would you like to suggest? Shayantan Shaha, are you there? Hello? Aryan Singh?
Sir, I think all one
No,
in the P bit.
see, sorry, come again.
One, all the P bits should be one, I think.
No, you can take that, I mean, but I'm just saying that see, you should. It is good to take the simplest input which will serve your purpose. If you take all p bits as one, you could do that, but that may be a little more difficult. So can you think of a simpler number?
1 followed by P minus 1, 0.
No, your input. See, you take, let us say you take 2 to the power p, that is, 2 to the power p. So now, if you multiply, 2 to the power p by 2 to the power p, what will be the result?
2 to the power 2p.
2 to the power 2p. So what does 2 to the power p look like? It is 1 followed by how many zeros?
P zeros.
1 followed by p zeros. Okay. So yeah. So now if you try to handle that using your so assume that your machine has p states. So how will your so if you try to design a finite state transducer, with so your finite state transducer has to go through how many states and then produce a 1. So it has to remember, right? You have got you got to remember that you got to output so many zeros. All right, you got to output so many zeros and then produce a 1. So now you apply the pumping lemma and see whether you have got enough states to remember that you got to, to remember the number of zeros that you got to output. So can you use that line of reasoning to, say that this really cannot be done using a machine of p states? Can you do that? Yeah? Can you do that? Are you able to do it? See, I think this you should have been able to do after, see, you have to output a lot of zeros, but now your machine has only P states. Okay. So, you output a 0. So basically, you are outputting a 0. You're making a transition and you're outputting a 0. But because your machine has only P states, say 1, 2, so at some point you are going to loop back, right? You're going to come back to an intermediate state. You're going to loop back. And the moment you loop back, you can't remember how. So the moment you enter a cycle, you can't keep track of how many times you have looped. You have no way to keep track of how many times you are looping. So the point is that you just don't have enough states to remember that you have to remember how many zeros you have output. So you cannot. No. Hello. একটু পরে আমার ক্লাস চলছে। Okay. So that is the argument. You just don't have enough states to remember how to output the required number of zeros correctly. So that's why you cannot design a serial multiplier, a finite state serial multiplier which can multiply any two numbers of any length. All right. So that is a basic limitation of finite state machine, or for that matter, a finite automata. So anyway, so this is an important aspect which you should remember. Note that what we just saw some time back, because these two are computationally equivalent. These two are computationally equivalent. So you could very well get into situations where you need to employ the principles of the automata theoretic principles in your for the design of your finite state transducers. In fact, we will need those concepts again now. So let us look at the issue of minimizing the number of states of a finite state transducer. So now we'll make a distinction between a fully specified machine and an incompletely specified machine. Okay. So a fully specified machine looks like this one, the one that you have here. Why is it fully specified? Because for each state, for each input, first of all, the transition is defined and also the output is defined. Okay. So here you can see that if you are in state A, you can just try to sketch the corresponding machine. So here you have how many states? You got 6 states, right? So let us just try to sketch the machine. I've just drawn 6 states. So let us call the states A, C. So now from A, on input 0 you go to E. So on input 0 you go to E and you also output 0. And on input 1 you go to D and you output 1. Now from B on input 0, you go to F. So B on input 0, you go to F and you output a 1. And on input 1, you go to D and you output. So let us see, you go to D and you output a 0. From C on input 0, you go to E. So from C on input 0, you go to E and you output a 0. And on input 1, you go to B and you output a 1. Then D, on input 0, you go to F. On input 0, you go to F and you output a 0. And on input 1, you go to B. Sorry, what did I do? I think I made a mistake. Yeah, from D on input 0, sorry, on D on input 0, you go to F, output is 0, and on input 1, you go to B. And you output a 0. Alright. And see, so this is, I'm just completing it. From state E on input 0, you go to A. So, this is, sorry, what did I do? E, on input 0, I go to C, sorry. On input 0, I go to C. And maybe I should write it somewhere else. And I output a 0. Input 1, I go to F. And I output a 1. And finally from F, I go to B on input 0. I am output 0, and on 1, I go to C. Alright. On 1, I go to C and I output is 0. Alright. So this is my machine. Alright. This is my machine. And it is fully specified. Why is it fully specified? As you can see, for each input, the next state is defined. For each input, the next state is defined and the output is also defined. So this machine is fully specified. All right. So sometimes we'll see that machines need not be fully specified. We'll see that later. So let us consider some basic notions of state equivalence. So two states, Si and Sj of M, are distinguishable if and only if a finite input sequence applied to M produces distinct output sequences depending on whether M is an Si or Sj. Alright. So basically you have a machine in which you have got two states, Si and Sj. Now, how will you try to check that these two, can you distinguish between these two states? So how can you try to distinguish between these two states? You can provide some input x, get a some x. I mean, so if you get two distinct inputs, then you can definitely say that, okay, on input x, I've got A here, I've got B here. So you could say that those are, different states. But if you have the same input here, if you have the same output, so immediately you can't say. But if they make a transition to, some other state, let us say y, and you see. So now you can see that, you are able to distinguish. You are able to distinguish. This is C, this is T. So now you are able to distinguish. Of course, in this case, you are able to distinguish in the very next step, but it need not happen so fast. It can, even this one might be the same, even this one might be the same. So even this one might be the same. So at some point, if you, you can have many transitions, and if at some point you have this distinction, so if at some point you have, so Z, you have say, I mean, if you have two distinct outputs, say E, and on the Z you have S. So then you can still distinguish. So long as you have a finite, sequence of inputs, these are your inputs. So long as you have a finite sequence of inputs, which lead to a different output sequence. So different means, of course, you are interested in the first place where it differs, because that is enough. Okay? So long as they produce, you can find two sequences which lead to different outputs for the same input, then you can say that these two states are distinguishable. So that is what is being said here. The Si and Sj of M are distinguishable if and only if a finite input sequence applied to M produces distinct output sequences depending on whether M is in Si or Sj. If you cannot find any two or if you cannot find any such finite sequence which will produce different output sequences, then you have to conclude that those two states are indistinguishable. Those two states need not be identical, but they could be indistinguishable. Okay, so that is the point to note. So that's when two states are distinguishable, and if you have two distinguishable states, then the sequence which helps to distinguish between these two states is called a distinguishing sequence. Okay, and then Si and Sj are k distinguishable if there exists a sequence of length k to distinguish between Si and Sj. And similarly, you have k equivalent if you cannot find a sequence of length k to distinguish between Si and Sj. And Si and Sj are equivalent if they are k equivalent for all k, all right, for all k, if those are k equivalent. And again, if you, so here the question is if your machine has n number of states, then can you put a bound on the value of k? So you will see that it is enough to consider sequences of length n minus 1. So if you cannot distinguish two states with suppose a machine has n states, you cannot distinguish those the states with sequences of length up to n minus 1, then really you cannot distinguish them at all. All right. So the underlying reason is again the fact that once you get back into a loop, then I mean you will just keep looping. So no matter how long an input you apply, if you cannot distinguish for k less than or equal to n minus 1, you won't be able to distinguish that. All right. So the way we can use that principle is that you can so you have so if we consider the example shown here, you have a machine with 6 states. All right. Now, so how do you try to? So what do you want to do? You want to. So suppose two states Si and Sj are not distinguishable. Okay. Then those two states are equivalent, right? Those two states are equivalent. So essentially, what you want to do is you want to partition the states of the fully specified finite state machine into equivalent classes, into equivalence classes, so that all the states in the same equivalence class are indistinguishable. Okay, that is what you want to do. You want to partition the states of this fully specified finite state machine into equivalence classes. So what you do is to start with, you assume that all the states are equivalent. You assume that all the states are equivalent, and then you see whether your claim is true or not. So let us see what we are doing here. I think we have actually we're at the end of the class, so I'll stop now. But I'll just show you the first step. So here, we have made we have assumed that A, B, C, D, E, F are equivalent. That is our initial claim. Okay, but is our claim true? So let us see. Now you can see that if you look at if you look at this, if you look at this row, suppose, so if you apply the input 0, if you apply the input 0 from A, you go to state E, giving an output of 0, and sorry, for input 0 actually you cannot make any distinction, right? Because if you give the input 0, no matter in which state you are, the output is always 0. But if you give the input 1, you find that if you give the input 1, you find that if you are in state A, you get an output 1. If you're in state C, you get an output 1. If you're in state E, you get an output 1. On the other hand, if you're in state B, you get an output 0. If you're in state D, you get an output 0. And if you're in state F, you get an output 0. So what is clear is that on input 1, you can distinguish between two sets of states, all right? You can distinguish between two sets of states. That is, so if you take A, C, and E, okay? A, C, and E. And then you can distinguish between B, D, and F, okay? You can distinguish between B, D, and F. Why? Because on input 0, for this set of states, on input 1, you get output 1, and for this set of states, on input 1, you get the output 0. So you are able to distinguish between these two set of states, all right? So that is how it goes on. You are able to, so this is actually P1, all right? So that way you can continue to reduce this partition. So we'll continue with this in the next class. All right, okay. So we'll stop here now. Thank you.